In this video, we are going to look at increasing and decreasing intervals with a rational function. So, the first thing that we need to do with this rational function is to find its first derivative. And so, I'll just kind of work over here to the side. Notice it's a quotient, so we will apply the quotient rule. So, I'll take the derivative of the top, which is simply 2x, multiplied by the bottom, which is x, minus the derivative of the bottom, which is just simply 1, times the top, which is my x squared plus 25, all divided by the bottom squared. And so if I go ahead and simplify this, I have a 2x squared minus an x squared minus a 25, all divided by x squared. And then that's going to leave me with simply an x squared minus 25 divided by x squared. Now, we learned that critical numbers come from values of the first derivative that make it equal to 0. And when you're talking about setting a fraction equal to 0, it's as simple as taking the numerator of that fraction and setting it equal to 0. So if x squared minus 25 is equal to 0, and I add 25 to both sides, then x squared equals 25, and when I square root both sides, don't forget the plus or minus, we get two critical numbers. X is plus or minus 5. Critical numbers also come from values that would make the first derivative undefined as long as they're part of the original domain. And so when we look at this, an x value of 0 would make the first derivative undefined, but when you look back at the original function, it's not part of the original domain because of the x in the bottom. However, you can get changing from increasing to decreasing at those values, which eventually become their vertical asymptotes on the original graph. So we will, when we're looking at our number line to test values, we also have to consider looking at the value x equals 0, since it is the value that does make not only the original undefined, but it makes our first derivative undefined. Okay, so let me come down here and I'll do my number line down here at the bottom. So we are going to look at values from or around -5, around 0, and around +5. So I'm just going to work left to right. If I plug -6 into my original first derivative, which is here, I would have -6 squared minus 25 over -6 squared. And that just simply becomes 36 minus 25, which is 11, over 36. And again, I don't really care about the value as much as I care about the fact that it is positive. All right, so then I need something in between -5 and 0. So I'm just going to simply use -1 and plug it into my first derivative. So -1 squared minus 25 over -1 squared. That's going to actually leave me with a -24 over 1. And again, what really matters is the fact that it's a negative value. Next, I need something in between 0 and 5. So 1 is always easy to plug in. And so when I plug it into that first derivative, 1 squared minus 25 over 1 squared, that also leaves me with a -24. So I get a negative value once again. And then finally, something bigger than 5, we could use 6. So we get 6 squared minus 25 divided by 6 squared, which leaves me with 36 minus 25 is 11 over 36. So that's a positive value. So what this tells me is that in terms of this graph, I'm going to be increasing from -infinity to -5, decreasing from -5 to 0, still decreasing from 0 to -5, and then increasing again from 5 to infinity. Remember, we talked about the fact that x equals 0 is a vertical asymptote on that original graph. So we do have to separate those intervals around that asymptote. So my increasing intervals, get back to a pen, my increasing intervals were from negative infinity to negative 5, as well as from positive 5 to infinity. Whereas my decreasing intervals are from negative 5 to 0, as well as from 0 to positive 5.